Thanks for joining, everybody. So I think I know most people in the room, and many of the people online. I'm Rudd Platt. As some of you know, I'm professor of environmental studies at Gettysburg College and a visiting scholar here at the Earth Lab for this academic year. So I'm really psyched to be here and to bring you some very special guests, Tom Kova. Tom and I was trying to figure out exactly when we met, but it would have been in the mid-aughts, I think. And for many years, we organized a session at the AGs on hazards, GIS, and remote sensing. And so we did that basically all the way up to when the pandemic shut things down. It was really fun. Tom and I got to bring in, and with other colleagues, got to bring in all kinds of scholars on that topic. So Tom got his PhD in geography at the University of California at Santa Barbara, and I believe worked with Mike Goodchild. Is that right, Tom?
Rick Church.
Okay, Rich Church. Excuse me. I'm sorry. And currently he is professor of geography at the University of Utah, and he is on the editorial board of the International Journal of GIS presently, and he has been involved in a number of research projects, including a recent paper on toward simulating dire wildfire scenarios, and I think we're going to hear more about that today. And he's also done an extensive amount of research on setting wildfire evacuation triggers. And so he has, and combining coupling fire and traffic simulation modeling. And so today he's going to be talking to us about ensuring public safety in fire-prone communities, the rise of dire scenarios. So thanks very much, Tom, for coming to talk to us today.
All right, thanks for having me. Thanks for the invitation. Okay, I'll just share my screen here. Let's see. Is that working?
Looks good.
Okay. All right, so as Rudd said, the title of my talk is Public Safety in the Wildland-Urban Interface. And that's just the broadest topic for my area. This is an image from the Oakland fire in 1991, and I just give, or from 95, the fire was in 91, but I just start with this so that people understand where I'm coming from. I was evacuated in this fire and lived in a community like this one. This is where the fire ignited, but I was about 2 kilometers south of this in a similar neighborhood. And that's really what got me interested in this broad area of evacuating the wildland-urban interface, was all the difficulties. And you can see, this was without the trees after the fire, so you can see it was a labyrinth of roads. That's San Francisco in the distance. And at the time, I really, just got fascinated, I guess, with the whole process and wondered where else this might happen. When I got to Santa Barbara and was looking for a master's thesis, I was still interested in this topic and talked to Rick Church, who I just mentioned, and the two of us came up with this sort of spatial optimization model for mapping population clusters in networks. And the idea was, how can we search for these neighborhoods like the Oakland Hills? And Santa Barbara had just had the Painted Cave fire in 1990, or right before I started school. So this area was familiar with large, really dire evacuation scenarios. And so this was basically a map that came out of that work. And you can see the red zones are the ones that have the greatest ratio of people to exits. We ended up modifying that to households to exits. It was just a simpler unit to deal with. And this one really was the one that caught most people's attention, Mission Canyon. And so this would have been about 1997, 95, somewhere in there. And that's a very high fire risk area, very high fire hazard. And so, this is looking at air photo development or air photo history of Mission Canyon all the way back to the 1920s, when it was just grass and some dirt roads, and then leading up to 1990. I think everybody that lives on the Front Range or anywhere really in a mountainous west area understands this kind of process and how these canyons get developed and the homes, incremental homes get added. Sometimes many homes get added or many housing units at one time. And they're often topographically constrained. And once you have structures in there, then you have no choice but to just do suppression. So you can see the vegetation from 1928 to 1990 completely changed. And so you end up with, a really, really difficult evacuation in a really high fire hazard area. For Front Range people, Colorado Springs, Evergreen, areas around Boulder, but there are literally thousands of these communities all over the West. This is looking at it so you can see it a little bit easier. This is 1938 and then 1990. Doesn't even include the development over the last 33 years. But essentially you have a community. It's the north part or the upper part of this image is much higher in elevation than the lower part. So this is on a very steep hill there on the side of the Santa Ynez Mountains. And the people at the top are on what's called Spyglass Hill, and you can look down on everything. And again, you guys are in an area where you don't have to be educated on this kind of development. It's just everywhere. It was, about 14 years later after this map was made that we had the Hasacita fire. And let's see, and so you can see the headlines: traffic deadlocked, evacuations confirmed. The pink area there in the lower left is the evacuation zone, and there's Mission Canyon, the area that I identified or that we mapped in 1995, right in the middle. Full-on freak out mode, fire forces more to leave home, traffic crazy. So yeah, it's not too hard when you have over 400 households with possibly anywhere from 600 to 1,000 cars leaving down very narrow, windy roads like the Oakland Hills and then also Mission Canyon, that you're going to have traffic problems. And so if this was static, at least we could start to map it and manage it. But as I said, it's just ongoing with urban planning or ex-urban growth. I think when I started this area, I thought this is going to be a big problem, but I really didn't even think about climate change. Didn't even think about changes in fire size or fire frequency or all the things you guys specialize in there. I was just thinking about that as a constant, and that it was really about just the development. But of course, when we look at the last 10 years, what a big, huge signal we get from the climate, right? From drought and wind events and everything like that. That's pretty much it on how I got into this. But now thinking about the wildland urban interface as a whole, it's really a national issue, right? It's not just a few coastal California communities anymore. It's really a nationwide thing. When I first saw this was from Wisconsin, right? The Wisconsin Silvis Lab. And just thinking about how much there was over in the east and up in the northeast, and not really ever thinking about that area hardly at all, really. This is just to show you basically how common evacuations are. A lot of times you'll see them in the news. This is in 2012. It's not easy. No one really counts these things. There isn't there's the National Interagency Fire Center that just does a great job with all statistics on the acres burned and the number of fires, and it's a rolling statistical count every year. But evacuations are sort of not anyone's real business. It's not really anyone's job. So we, one summer we counted from April until November, just using the media, just Googling around. We found 124 in one summer. And some of these were huge, like the Waldo Canyon fire was that summer in Colorado Springs. That was 30,000 people. It's on the map there, but some of them were just a few hundred campers from a campsite. And I think actually that we've had some bigger years since then in terms of just the sheer number. And if you expand it to include Canada and Portugal and Australia and Greece and all the other countries that experienced them, it would be in the hundreds, if not thousands, of evacuations every year worldwide, just from wildfire. Um, Thinking about the dire scenario, and that's the topic that I mentioned, or that Rudd mentioned, so I'm talking about today. For me, it was really the Two Chimneys fire in 2016 that so I was like, what is going on? November in Tennessee, and you've got 14 people dying in a fire. And so it was way outside the envelope for me on locations. It was outside the envelope in terms of the season. And then it was outside the envelope in terms of the fatalities. Another one was the Tubbs fire in Sonoma in 2017. And this one also killed, I think, about 14, might have been about exactly the same, really. And so, this is starting to show up as what's going on here. Then came, of course, the Camp Fire. That's the mother of all dire scenarios, and that one was what, 85 people. And here's a video cam or dashboard cam of somebody evacuating in the campfire. It was essentially a ginormous community burnover. Really, I mean, burnover is a term drawn from wildland firefighting, when fire burns through and they have to deploy their shelters. But this was a community burnover, as you can see from this dash cam, that thousands of people were evacuating really in the fire. That's the worst case scenario. You really want everybody out, obviously. So digging a little deeper, what happened with the Chimney Tops fire, Chimney Tops 2, you had the stage was set, exceptional drought, wind gusts 40 miles an hour, burned 2,460 structures, 14,000 evacuated. The EOC phone system did lose power. So that's one thing to think about. A scenario can become more dire in situations where you lose power or the warning system. But here, Sevier County officials admit fire evacuation alert not issued. So we had a situation where, of the 14 people, there was a lot of confusion in the town of Gatlinburg because a fire alert wasn't really issued in 2016. Many Gatlinburg residents and visitors to the tourist town have complained they received no mobile alert notification to evacuate. So lots of people didn't ever receive any warning about this fire that really started 6 miles away. Here's the Tubbs fire one. 22 fatalities, excuse me, not 14, a few more than Gatlinburg. Major evacuation the evacuation systems they used were Nixle and SoCo. Sonoma officials could have sent out an emergency alert to every cell phone in the region on Sunday night, but chose not to, saying that such widespread alarm would have hampered emergency efforts. Researchers, and many of them out of Boulder and other people affiliated with the Boulder workshop, have been fighting this for 50 years, basically. The hesitation on the part of emergency managers, fear of panic, fear of confusion. We don't want to warn them, and then withholding information. So this is just the wildfire example, but most of the cases I think that have been studied are not wildfires. And then the Camp Fire, most deadly since 1918 in Cloquet, fire in Minnesota. 86 fatalities, 12 injuries, 18,000 structures. In June 2009, which was 9 years before this fire, Butte County civil grand jury concluded the roads leading from Paradise to the Upper Ridge community had significant constraints and capacity limitations that limited their use as an evacuation route. So they had various exits and heading in different directions, but they weren't suitable for evacuation. There was really only one way out, Skyway Road. And so I mean, just to give you an update, I know they got a giant grant this year or last year to improve some of these roads. So they are going to do a lot of road construction. But in this case, it was partly to do with egress and constraints on egress, sort of like the study I showed you at the beginning from Santa Barbara. They did make the best use they could of Skyway Drive. They reversed some lanes out It's called contraflow, so that they could actually increase the capacity of the road. So that was pretty novel. This is what it looked like essentially if you were trying to leave. It looked like nighttime. This was in the middle of the morning. Those were tail lights. It just looks like the middle of the night, but it's just because it's covered in smoke. They had a staged plan, which was pretty clever. It sort of got overridden because there wasn't really enough time for them to carry it out in a methodical fashion. But they, in terms of planning, they had a fairly good plan. This is a very experienced community. They had, well, I don't know, at least 10 fires, 10 near misses in the 20 years leading up to this one. The town of 27 plus, gotta move something here for a second, did everything right, including an evacuation drill this year, and still could not thwart the rage of this inferno. So you have a case where a community really should get an A for their preparedness and planning and everything they did with the contraflow and the staged evacuation, the warning systems and everything. But sometimes the situation is just too dire. So really, this one, the dire scenario formation here, was a product of the time available. So the ignition occurred from the time, this is hindsight, really. We get to go back and look at this with hindsight. It's far harder to deal with this in real time. But they had about 1.5 hours between the ignition time and when the first home started burning on the north side of town. And their evacuation plan was at least 2.5 hours. It was really 2.5 hours. So even if they had made an instantaneous decision to evacuate the community when the ignition occurred, they still would have been an hour underneath what they really need to do it methodically through all their zones, right? I think they had 26 zones. So you have some cases where it's dire from the get-go, and really there's not much you can do to undire it to make it less dire. And so this was really the point where I thought that we could start studying dire scenarios themselves. They seem to be occurring more and more. They become dire for different reasons, sometimes decision-making, sometimes the duration. What I'm talking about here with duration is how much time is there to act. So that's the biggest factor in terms of predicting the direness of a scenario, is what time. Are we talking about a day, a week, an hour? That's really the main factor. Second is the decision. I showed you a couple cases there with the Tubbs fire and chimney tops where they had a fair amount of time, but through decisions to not warn or system failures, people did not receive the alert quick enough. And then design, the community design. So like the Oakland Hills, Paradise, Santa Barbara, we design communities that make it really challenging to get everybody out in a hurry at the same time that we're seeing urgent scenarios that require everyone to get out in a hurry. So here's an example from an opposite end of the spectrum, the Cerro Grande fire. And I don't know what to do with that thing. The Cerro Grande fire in Los Alamos in 2000, they had a week. How do you end up with a dire scenario when you have a week to get ready? And they did do a lot of amazing things. And this really is a model a little bit like Paradise. I think they did a great job. Their plan was really sophisticated for how to get everybody out. But they waited. And I think, like with Paradise, emergency managers, they don't want to disrupt communities for every little fire. And also they were hoping it would either not make it to the community or change direction. So you hope for favorable changes in the fire, but then you're also burning up the clock while you wait for those favorable changes, and then suddenly you do have a dire scenario. So it isn't just the time available that can be used to predict the direness. And so this was the question they had all the time for that whole week. Should we issue a warning? Should we evacuate? So dire scenarios, dynamic and uncertain. Rudd mentioned trigger points. Yeah, that's something we've worked on a lot. Thinking about where's the best place to set a trigger so that when the fire comes towards it like this and hits that point, you say evacuate. Usually, and then you want to know that it's going to guarantee you a minimum amount of time. Usually those are ridge lines or prominent features, roads, water bodies, what else? Yeah, rivers sometimes, but not always. And so here's your scenario where we have a certain amount of time available and we have a certain amount of time we need to evacuate people. The problem, I guess, is in this case, we don't have a dire scenario. We have more time than we actually need, which is good. But there's a lot of uncertainty in these estimates. And I think this is one of the problems that we've seen in a lot of these fires, like Paradise. They didn't know how much time they had. There isn't really, that was some really fast moving fire. They did wait, they waited at least an hour for it to hopefully go a different direction. It didn't. Like a little bit like the Cerro Grande case, you see history repeating itself. If you think about these as uncertainty bars, then maybe that's the actual scenario. That's the other extreme where you're actually, it's going to take longer to evacuate than the time you have available. You just don't know because of the uncertainty and the fire behavior, as you guys are more than aware of there. The fire behavior can be crazy and way outside the envelope of anything anyone's ever seen. And so it isn't simple enough to say whether the scenario is dire with this level of uncertainty. The paper that we published on this was we wanted to create an index or a score to be able to say not just it's dire or not, but how dire or how undire. And so here's 4 categories. The index runs from -1 to 1, or actually higher, but it's most of the time it's going to be in the range of -1 to 1. A routine evacuation is where the evacuation time is less than or equal to lead time, and that's the time available. It becomes dire as soon as your evacuation time is greater. If you're more than 50% greater than the evacuation time or the time available, let's say you have an hour available, it's going to take you an hour and a half to get everybody out, then you're in the Paradise scenario, very dire. And then extremely dire would be one where it's going to take you like 2 hours to get everybody out and you only have an hour. But as I mentioned with uncertainty, this is all theory, this is academics in a journal, right? Is that, you really don't know which one of these boxes you're in when you have an actual scenario in play, right? So you can estimate, but you're estimating 2 variables and both of them are highly uncertain. This is a figure from the paper basically thinking about the anatomy of how things can change. So another point I want to make, a really valid point, or sorry, important point, is that scenarios you don't just classify them at the beginning and then they stay that way. They can get more dire or less dire in the middle of the scenario. So here's one. If you look over at the y-axis, you have a fire ignites 2 miles away from a community, traveling at 1 mile an hour to the community. So it's pretty easy to calculate that you have 2 hours before fire will be entering that community from the edge, right? You also have an evacuation time at the start of 1.5 hours. So from the very beginning at 1 o'clock, this was not a dire scenario. You actually have 30 minutes more than you need to get everybody out. Unfortunately, and we've seen this in a number of fires, at 1:30, a tailwind kicks in and triples the fire spread rate. And a good example of that is the Yarnell Hill fire in Arizona in 2013, where they told people, you have an hour to get out. And the fire was burning their homes in 20 minutes. And that came through a microburst above the fire that tripled the fire spread rate, triple the rate, divide the time available by 1/3, right? So without maybe anyone even realizing it, see that yellow dash line dropping down. Now you only have a half an hour available, but you're halfway through your evacuation at that point. But you still have a lot more people to get out. Has anyone, just because of that tailwind, has anyone in charge realized that they are now underwater? At some point, you can also officials can take actions to reduce the direness of a scenario. In Paradise, they designated temporary refuge areas for some cars in parking lots where they realized we just can't get all these people out. Let's move some of them to parking lots where we can set up a defense. And so that's what I tried to mimic here is officials open a temporary refuge, and that reduces the overall time. First, you're protecting some people in the parking lot. Second, you're reducing the delays in the traffic by getting them off the road, which allows the people on the road to get out quicker. But overall, they didn't make it. They came in with that red bar there showing that the fire arrived at 2 p.m. and they still had a small percentage of people in the community. So maybe this isn't the most optimistic scenario, but it's just as likely that the wind will change and send the fire in a different direction, or the wind will die down and slow the fire. And so you can have scenarios that were started extremely dire and would go through the reverse process here and become much less dire halfway through. So I guess this figure is redundant, but it's just that gray arrow to show that things can move back and forth between these four categories during the fire. So not just before or after. So what can we do essentially to reduce the time on the evacuation? It's hard, not much can be done with fire suppression in some of these big fires. But what can we do on the protective side? Well, these are the phases that you would find in a textbook. The incident ignition detection time, how long does it take to figure out there's a fire? That's pretty short these days with cell phones, because the 911 operators get inundated with calls about a smoke plume pretty quickly. The one exception is nighttime. So the Tubbs fire is a good example of it. How long did that thing burn before somebody reported it? If it's dark and everybody's indoors, they're not going to see the smoke. Decision lead time, I pointed out, it can be infinite if they don't make the call to warn people, right? But that's the time it takes for officials to assess the fire and then decide what action needs to be taken. The warning time, and we know from cases I showed you that they do practice wait and see, we call it, where let's wait and see. It's pretty obvious what that means. Warning time is the time it takes to alert people, and we're benefiting there from technology, from technological advancements like wireless emergency alerts. When used right, can really get the word out, and also reverse 911 and subscription-based systems. Preparation time is the time it takes households to gather their stuff, pills, papers, prescriptions, whatever they need to gather together. And that's often the focus of a lot of evacuation planning, is telling households, get that go bag by the door. It's fire season. We have a red flag warning coming up. You could be asked to leave. And then network clearing time, that's the traffic management issue, all of the things about reversing lanes and so on. And the total sum of those is the evacuation time. So here's a non-dire situation. And that would be the fire arriving there over on the right. It happens after everyone's out. And then here's the dire situation where, like in Paradise, you still have a certain percentage. It looks like about half the people are still on the roads when the fire enters the community. So what we want to do is shorten all those phases. And so really that's what I'm going to talk about, is just the different efforts that are going on research-wise and in practice towards reducing these times, these overlapping intervals, to get something that is where people can get out quicker. And then problems can occur in multiple time phases. So it isn't just that warning time was a problem or preparation time was a problem. You can actually have a fire like the Paradise fire where you had problems with the lead time, decision time on the part of officials. You had difficulty warning people because subscription rates were low, like in the Marfa fire, as everyone knows there. Some households were ready to go, others weren't. With 26,000 people, you're going to have a pretty big distribution of preparedness, right? And then network clearing, of course, was a constraint too. So in some of these cases, it's not just one thing, but many. This was kind of a dashboard that we proposed. Essentially, there's 4 scenarios here, each row 1 through 4. And thinking about where is the problem? What's the bottleneck? I think that when you say bottleneck, oftentimes people think about traffic bottlenecks. But of course, you can have a bottleneck in warning people. That would be like one every third home is getting a warning, but the other two aren't. That would be a warning bottleneck. Or you can have a bottleneck up in the decision time with the officials. And so that first scenario, there were some mild problems with figuring out where the ignition location is, or sorry, problems with the ignition location being too close to the community, but not terribly close, just closer than you would like. Fire spread rate was a problem, but not a huge problem. Public response turned out to be an issue. People didn't perceive the threat as that big. And then maybe there were some mobility issues with either latchkey children at home without a car, or elderly people, disabled people, often, any kind of mobility issue. The second one, things get a little more dire. Now we have a really, really rapid fire spread rate. There were problems detecting the fire. Maybe it occurred at night. Official decisions were hampered by the fact that it was night and the EOC wasn't open. But everything else seemed to go pretty smooth, and on and on. And then the bottom one is just one where, whoa, everything went wrong. There was all factors were against the scenario from keeping it from not getting dire. I should point out something here that I didn't think about too much until after the Marshall Fire, actually, and that is all the favorable things that can happen. In the Marshall Fire, I don't know if we have colors for this, maybe it would be taking some of the red to green, but the altruism displayed by people taking care of neighbors and taking care of family and was really unprecedented, in my opinion. And also the tremendous number of people they had. The law enforcement and firefighters were over 300 people, right, according to the after action report. So that's a great example of where it's not all forces against you. There are also forces in your favor. And sometimes those can be really surprising, like the altruism. Actually, in Australia, they call that volunteerism, but it's the same idea. It's people placing the needs of others ahead of themselves in a disaster, in a wildfire. And so, that kind of thing gives me hope, gives optimism out there that people can take care of each other, look out for one another, text each other outside of officials and so on. So this was the slide that, thinking about the Marshall Fire and other fires where an ignition occurs and it just blows your whole plan right out of the water before you even start. You had your trigger point set. It was going to be this road or it was going to be that ridge line. And you had your evacuation plan taken care of in your stages, and you're going to use wireless emergency alerts and everything. And then you get this. And so this is really a tough one for the future in terms of, proximal ignitions to communities. And it's just inevitable. As you spread out into the wildlands, there's just more communities out there and more people. A fire that would have been far from some urban area 30 years ago is now right on the edge of the development. It wasn't really the fire that changed location, it was the development. There's a lot in this slide, but all I wanted to just say is that we have studied warning triggers from a cognitive point of view. This is work was done with Frank Drews, thinking about all of the factors that go into the setting of one of these things. There's natural factors, the dynamics of the threat. In wildland firefighting, they often want to know the flame length. That's one of the most important variables to them, not necessarily where is the fire or how fast it's moving, but how tall a flame is the flames are we talking about here is one of their first questions that we found they wanted to know. We ran human subjects, incident commanders, through what's called process tracing, where they have a matrix of variables in front of them on the screen. But they have to click on each box to see what its value is. So it might say like fire spread rate, and they can click on that, and then it will turn it over and show them the fire spread rate. Some of the factors are dynamic, so they'll have to go back and peck on it like a hamster trying to get a pellet to figure out what is it now. And others are static. And to make this shorter, we found that the experienced firefighters, these are people that had managed over 70 incident commanders, over 70 fires in their career, were constantly going back to those fire behavior ones. They were just like, what is the flame length again? What is the spread rate again? And the junior incident commanders, we would only call them less experienced because they are experts too. To become an incident commander, you have to go through a lot of training. So just less experienced. They were often looking at the community. What sorts of homes are in the community? What's the structure type? Where are the exits? And these are static factors in the context of a fire, right? They're not changing. So it was one of our more interesting findings was experienced firefighters. They really want to know what's going on with the fire behavior, fire spread, evacuation behavior, very interdisciplinary area. So we have done an extensive amount of coupled modeling of these systems. This one, looking across the top, traffic simulation models get integrated with fire spread modeling. We have community data about the distribution of the households and the roads and shelters and exits and so on. We calculate evacuation times and fire travel times and try to figure out where that trigger should be placed. So when the fire comes over the ridgeline, will that offer enough time? We don't know. I think we try to answer those kinds of questions. The traffic ends up with vehicles moving through mostly in agent-based kind of micro simulation systems. We generate fire perimeters, project forward, and as well as trigger buffers. And when the fire hits the trigger buffer, that's the point you want everyone to start evacuating. This is kind of what they look like more graphically. You have your traffic model. On the left, you have your fire spread model on the right, and your community in the middle. And we're looking at, there's a fire ignition in red, the red dot up there, and we've got time 0, time 1, time 2. That thing is coming towards the community. The trigger buffer is the sort of opposite. It's the black dash lines. And so one trigger might be when the fire reaches point T0, and that's your outer trigger buffer to offer the most time. That might be the best time to tell people to leave. Oops. So yeah, here's a fire perimeter. We were working in Julian. It's kind of a softball, I don't know, T-ball kind of case study because Julian is such an island of a little community. When you think about San Diego County, and fires can occur anywhere, and there's sprawl all over the place. And a lot of the fires they manage are much more complicated than a single fire coming towards a community like this shown in orange, but it makes for a simpler case study for simulation. So yeah, there's the fire and there's the predicted perimeters. And this is like coming up with evacuation buffers that offer different levels of time. So 160 minutes, 128 minutes, 88 minutes, 53 minutes. A decision maker could choose among these and say, yeah, 53 minutes is enough, or I want 2 hours. And so then you can hopefully give them an idea. Tons of uncertainty, as I mentioned before, even with the modeling. Maybe the modeling doesn't even reduce the uncertainty in terms of the estimates of the time available and the time it'll take to get everybody out. But at least we can run scenarios, we can run simulations, what if scenarios, and say, what if the fire was traveling at this rate? What if the people left at this rate, and took this many vehicles? But we have to admit that we are just in the ivory tower here, and these are not systems that are ready for real-time decision making, to actually be in the incident command center running this kind of model. It's just hasn't happened yet. Maybe someday. Okay, that's sort of the decision point. The warning phase. So the big advancement here is wireless emergency alerts. Really, that's the game changer. The instantaneous, it comes by radio to our phones. You've all had Amber Alerts before. And so essentially it's just using the same system, but for fire. So this is a paper that came out like a few weeks ago. We called it Ember Alerts, where we assessed 2 years of wireless emergency alert messages. This was done with Erica Kulagowski and Nicholas Waugh and Jeanette Sutton. 2 of those people are from Boulder Sociology. And we content coded according to Dennis Milletti's warning response model to see how are officials doing. It's like grading them essentially. This is like a rubric for grading you for a course, but we're grading incident commanders or law enforcement, sheriffs, who's ever sending out the messages. And we're also really interested in the 90 versus 3 character differences, because in the last year, during this time frame, 360 character lengths were being offered. So there were some using 90, some using 360. So Miletti's content elements are the name of the hazard. Did it say there was a wildfire? Description of it, like where it is, how fast it's moving. The source of the message is the officials, coming from the Butte County Sheriff. The guidance, what action should be taken, the impact before it arrives, the time they have available, essentially, the expiration time of the message. In other words, this is only good for another half hour, and then the location of the hazard. And then there were a couple, Meletti had a couple style elements too, abbreviation and acronyms, and then hyperlinks. Another nice thing of the advancements in WIA with the 360 character limit was it also added hyperlinks. So you can now say, for more information, go to, and then a tiny URL. So one of the first things we realized in looking at the messages was, how many different ways there are to tell people to leave. If you're in Oregon or Washington, they're crazy about level 1, level 2, level 3. One of the things that I noticed in researching this was they never can really just say level 2 without describing what it is, because they can't be sure that everyone out there, tourists and visitors, knows what level 2 means. So whenever they do give a level 2, they will follow it up by saying, this is a set. This is set in the ready, set, go model. You must have your car loaded and your pets gathered, and so on. Now, there's also Ready, Set, Go itself, which is popular in a number of states. California, I'm getting mixed up now, but I know California is one of these with the evacuation warning, the evacuation order. So a warning is what would be called a set or level 2 in some other states, but it's called a warning in California. There's other places that have voluntary evacuation, mandatory evacuation. There's some states that use pre-evacuation, which would be equivalent to the warning or level 2. So they almost all have 3 levels. They just name the 3 levels different things. And so why is this a problem? Well, imagine a fire in 4 corners where you have New Mexico, Colorado, Utah, and Arizona, all in the evacuation zone. And all 4 of those states use different messaging methods. And so if you're sending out wireless alerts, you can't stop them at the border, right? If I want to send out a WIA message in Arizona, I can't tell the radio waves, please stop at the Nevada border. So people would be getting all sorts of confusing things. So one of our goals with this paper was to, hopefully raise awareness at the national level that it's, sometimes states' rights and autonomy is a good thing, but in terms of fires that occur on cross jurisdictions and stuff, this is nuts, basically, to be blunt. Here's some findings. So you can see the figure 1 here, the 2 things. That's just showing that most of these things get sent out in the summer. It's or in the fall, early fall. So there's a WIA cycle for fires. And this other one was sort of the sobering results of how many of those Meletti elements people were subscribing to. The mode was 3, so 3 out of the 8. Nobody had all 8. We never found a single message out of all those 1,200 messages where people had really gotten an A from Meletti, basically. There was only a very few that had 7, a couple that had 6. And so, yeah, there's a long ways to go in terms of helping people learn how to use WIA in the most effective way in terms of research results. This was a little more promising. This is kind of showing that when you do give them 360 characters, the number of elements from the WRM model do go up. So you can see the dark ones over on one side, that's the 90 character, and then the lighter ones over on the right side. So the 360 character limit is going to help. And of course, so is the URL to more information. That's really all I had to say about the warning phase. There's other research going on, but that's one that we're working on. In the public response phase, really the huge thing now is GPS data. GPS data is kind of opening up a whole new window into evacuation. So just to show you here one product, this is a evacuation compliance rate map by block group. So this is nothing we could have ever done. It would have been very expensive, I guess. It could have been done with traditional surveys, and then asking people something about their location. But really with GPS, we don't have to bother to let people respond. We can just tell them, we can just get the ping data from a cell phone provider and then map. And you can see the darker areas are areas where people complied more, and the lighter areas are people complied less. So new data to ask new questions. We also discovered evacuation shadows. If you haven't heard of that, it's when people outside the evacuation zone leave even if they weren't ordered to. It was something that was discovered during 3 Mile Island in the 1970s. And it's also been documented in some hurricanes, but we were the first really to document it with mobile phone data in the Kincaid fire. That basically there was quite a big pulse of departures from people on the edge of the evacuation zone in Sonoma County, even though they were not officially told to leave. It can be a problem, like in Hurricane Rita, where you get an extra million people leaving, really blocks a lot of the traffic. But in this case, it wasn't something that would really disrupt the traffic flow. Just interesting. In the mobility phase, this is from the Waldo Canyon fire. I mentioned, I'm kind of speeding up here, but I mentioned the Los Alamos evacuation plan. I still kind of hold it up as a model of really what one of the best plans I've ever seen. But you had stages, which I mentioned, were getting the people greatest of risk out first. You can see where the fire is coming from. They controlled the intersections. They basically, if you don't take any action in an intersection, you can have 16 different ways to collide. If you block the entrances, you can reduce that dramatically, which they do. They don't let people drive in when they're taking people out. You can induce a merge, but really what they did in Los Alamos was this kind of thing, putting in what we call it a continuous state of flow. And that picture from the Waldo Canyon fire, that's what they were doing. They had a really large volume of people coming down from mountain shadows, and they wanted to put it in a state of uninterrupted flow. So block the freeway, ignore the traffic lights, and just get everybody moving. Like it may have happened to you after a sporting event. They do it like after football games and so on. Bailey, Colorado. So this is a community near Bailey. It's not Bailey itself, but some people contacted me. They had 2,000 homes up a canyon there. That I think it comes down to 285, the main road there. And if you're an evacuation planner, you're like, OMG, as you guys say, what are we going to do with potentially 3,000 to 4,000 cars, or maybe even 5,000 cars coming down one road and there's background traffic on the main road too. So some places have been forced into shelter in place. They just have to. It's just the way the place is built. You can't get everybody out. So this is like a school they had. So we were looking for parking lots, water bodies. It could be bad. And hopefully the fire would be far enough away and this would never be needed. But you have to think about that dire scenario. I'm running out of time, but in terms of actually using fire shelter, we have a couple greatest hits in the U.S. We have the Verona Casino in 2003. And we have the Westmont College Gym in 2008. The first one there was about 300 people. The second one was about 900 students from the Westmont College. And both these cases in the Verona Casino, they just told people to stay put. So one thing we do in the U.S., even though we may not recommend people travel to a shelter that often, if people are in a shelter, like a school made out of cinder blocks surrounded by a parking lot, there are many cases, including in Colorado, where schools have been told to stay put and parents have been told to stay home. Do not come try to pick your kid up during this fire. In the Westmont College Gym one, that was really fantastic. But just by coincidence, about a year before this fire, they had decided the gym would be their shelter and that students would just walk to it because they had realized they can't get everybody off campus. Abroad, if you look at Australia, they do a lot of work with stay and defend in terms of people sheltering in their own home and defending their own home. Not so common here. It's done. Actually, Sarah McCaffrey and Travis Paviglio have documented a lot of it. There's a lot of people defending homes, but it's not something that officials have recommended. Okay, last slide. This isn't even my project. I just wanted to throw it in because it's so interesting. But Berkeley is leading a multi-campus project associated with developing serious games. It's a whole new generation of things where we've always viewed simulations the way I showed them before, where we would be an input into decision making. And this is going to be actually video games for training decision makers. So they will have to, I'm guessing, I'm not on this team, but they will have to formulate the warning message. They will learn from mistakes instead of having to wait for things like Gatlinburg or Sonoma in the Tubbs fire. They can learn from their mistakes. They can be given more and more difficult scenarios, more and more challenging. And so really from the point of view of dire scenarios, you can train them. This is a whole new approach to simulation. There's Oakland to wrap up. That's what it looked like a few years ago when I was there. And you can see a lot of the trees are coming back. The homes are rebuilt. And so, disasters recur. Fortunately, they had a ton of rain this year. So this isn't going to be one of those years, but, somewhere down the line, we may see that scenario again. In summary, recent extreme fires outcomes have taken a turn for the worse for various reasons: close ignitions, delayed official decision-making, poor egress. Problems in all evacuation phases are still common. Wish that wasn't true. There's a need to dramatically step up wildfire protective action planning. So because of cases like Paradise, the Marshall Fire, Tubbs Fire, and all these other fires, that we are just not up to the challenge yet. Climate change is ahead of us. It's throwing us curveballs that really we are not really geared to deal with. Thanks.
Can you hear me?
I can.
All right. I have two questions about the traffic modeling in particular.
Yep.
One is about existing background traffic. So like in the case of the Marshall Fire, we sort of evacuated everyone into urban Denver during evening rush hour. And then the second one would be, so the more important one to me is about your destinations. So if we have origin destination pairs of people leaving their house, when you're simulating, where do you simulate that they go? How far do they need to go to find a safe place? Where is a low hazard area, specifically in your simulations?
Great questions. And the first one really about background traffic is a traffic management problem. It's really a challenge. But I know about the Marshall Fire, but I think they did the best they could. But what should have happened is 36 should have been blocked in both directions. Sorry, folks, but you're just going to have to sit in your car like people do when there's traffic accidents on the freeway, right? When the risk is that high to a group of people, and this would have been people on the west side of Superior and Louisville, right? You have to just, basically block people from entering or going through in background traffic. It's pretty common, but it's not universal. On the second one, I never thought of having a few exits as a positive, but when I look at cases like the Cerro Grande fire, I realize the destination choice becomes really simple when there's only one way out. Really, so in some of our modeling, we're modeling low egress communities like Paradise to begin with, and there aren't really a ton of options. I think where you would see what you're talking about might be like the Ramona fire or the Witch Creek fire in San Diego. I mentioned San Diego. It's just such a sprawling. There's more people in San Diego County than the entire state of Utah. And the fires can occur everywhere and go all different directions, and roads in all different directions. And so we just make assumptions. Modeling is just rife with assumptions about people will go to their closest exit or people will go to the biggest exit. And I'll admit that we often don't simulate background traffic. I think it's talked about more in research papers than it is actually simulated. It really would make things look bad. One other point I forgot to make really is that when people are running simulations and publishing articles or even just presenting plans to communities in real life, they never really want to show a really dire situation and say things like, and so 20% of the people never got out, really. So that was one of our points in the dire scenario paper was, and hopefully in this serious gaming project, is let's not be afraid to throw fast pitch scenarios at ourselves. We have to stop playing t-ball and soft pitch with all of our scenarios so that we can say, ta-da, my model gets everyone out with more than enough time. Really, we need to start having, I mean, actually Brian Wolshin from Louisiana State did a study once in Utah, of all places, just near me, where he did calculate percentage of traffic that didn't get out. And I think when he published that paper, I always thought of that as being casualties. But now that I've seen how many people could get out in Paradise, I think, no, we don't really know. You can actually have fire burn right through communities and still lots and lots of people get out. So even if you say 20% can't get out, it doesn't necessarily mean that's 20% casualties.
I guess I had a couple questions and trying to remember what they all were, but one of them, I guess I'm curious about your modeling. You referenced that there's large uncertainties on sort of both the fire arrival time and the evacuation time, but I'm curious if that's something that the models can help out with, is putting some numbers on what the uncertainty might actually be in different areas.
Yes, yeah, and I think in the paper, this is from a prior student. He's at South Dakota State now, Dapang Lee. In the paper, he did so many simulations that he was able to come up with uncertainty ranges. So, yeah, but I mean, everybody there knows fire modeling. We're using Flam Map related to Farsight, and I'm not a fire modeler, but it's not really built for fires like the Marshall Fire or the campfire in terms of all the chimney effects and 60-mile-an-hour winds and flue things. And I'm not a fire expert, obviously, but that's one thing I do hope and I think will happen, is that we will get there's still stuff like Janice Cohen at NCAR with the $2 million model. If you can raise $2 million, she can run a model for you with a fire atmosphere coupled model. But maybe someday we'll have a cheap, free kind of public domain, really capable fire model for fire spread modeling.
One more. Thanks for a great talk, Tom. This was really interesting. I'm curious, so you did, it sounded like you talked to incident commands and got some qualitative information from them for your studies. And I'm wondering, like, if you've seen in your research or other research, how suppression and the human decision-making aspect from a fire suppression standpoint is in models. I'm thinking about just like resource allocation and decision-making and like how we can account for that part of the equation. Yes.
I'm not sure I got the question clearly. What is it?
Yeah, so my question is whether or not you've seen like suppression, decision-making, incident command integrated into some of these evacuation models. If that's something that can be done, or how that might look.
Okay, yeah. No, we're terrible with suppression. It's almost like those people aren't even in the game. I guess you could simulate it by, temporarily slowing down the fire. A lot of the most dire fires, suppression is not really an option. But we had a great example here with the Parley's Canyon fire, July of 2001, right here near me, between Salt Lake and Park City. It was a total coincidence that the county mayor, Salt Lake County mayor, had an unlimited amount of aircraft here. It was just Salt Lake is a kind of a way station during the summer, nice and central in the western US, to send, all the different aircraft to different fires. And so it was just a coincidence. There was a brief downtime then, And they had planes at Camp Williams, planes at Hill Air Force Base, planes at the Salt Lake Airport. And I don't know if you want to go watch some amazing videos, watch the air attack for the Parley's Canyon fire. Just they were flying DC-9s like they were biplanes, or DC-10. I'm not a good DC expert. They were flying big planes, and they were flying them like they were little toys. It was incredible. My cousin is a pilot. He couldn't believe the dives they were making, but they stopped it. They stopped the fire before it got to Summit Park, which was all wood homes in forest, just like Evergreen, and you're familiar with it. And they stopped it just basically hundreds of yards from the edge of the community. And the mayor said it was the aircraft. Basically, I can't believe I had that much aircraft at my disposal right in my own backyard, because probably a week later they would all been deployed to some other fire. So it's a factor, but I have not seen anybody really trying to incorporate it into this kind of coupled model.
All right, Tom, I think we're at time. I really want to thank you for this great talk, and a round of applause for Tom Koga.
Thanks, folks. I follow your stuff there. It's amazing.